governors. We'll see why the governors are used and where do we use it, and rest of the function. The function of a governor is to regulate the mean speed of an engine when there are variations in the load. Right? So with the variation in the load, we know the engine speed may change. Right? If we increase the load, the speed may decrease, and if we decrease the load, the speed may increase. So in order to maintain, right, we use governors. When the load of an engine increases, its speed decreases, and therefore it becomes necessary to increase the supply of working fluid. Right? So we know when the load is increasing, right, speed will automatically reduce, and therefore we need to supply extra fuel in order to increase the speed. On the other hand, when the load of an engine decreases, its speed increases, and thus less working fluid is required. Right? So when the load is decreased, we know the speed will increase. Right? So in that case, we don't need much fuel, so the need of the fuel should be decreased. The governor automatically controls the supply of working fluid to the engine with the varying load conditions and keeps the mean speed within certain limits. Right? So this is the use of governors. So they maintain or automatically controls the working fluid and thus control the speed or keep the mean speed within a certain range. Right? A little consideration will show that when the load increases, the configuration of the governor changes and the valve is moved to increase the supply of working. How the functioning of governor is. So when the speed or load, right, when the load increases, then the configuration of the governor. So it is designed, the setup is designed in a way there's a valve which will control the flow of the working fluid. I will show it in the diagram. Right. Conversely, when the load decreases, the engine speed increases and the governor decreases the supply of working fluid. Right. So this is how the functioning of the governor is. So by supplying or controlling the working fluid, it controls the speed. Right. So there are a few types of governors. Right. First is centrifugal governors and the other one is inertia controlled governors. Right. The governors may broadly classified as first centrifugal and then inertia governors. So this is how the classification of the governors will look like. Right. So centrifugal governors may further be classified as follows. Right. So this is a classification of centrifugal governors. Right. We have inertia controlled governors also. We are not going to discuss them. Right. So this is solely about centrifugal governors. In centrifugal governors, there are two types: pendulum type and loaded type. Okay. We know the pendulum clock, right? So it is more on that type and loaded type. Pendulum type, there's a governor called watch governor. Right? And in loaded type, there are again two types. One is dead weight governor and the other one is spring controlled governor. Right? And within dead weight governor, there are two types: Porter governor and Royal governor. Okay. And in spring controlled governor, there are four types: Hartnell governor, Hartung governor, Wilson Hartnell governor, and Pickering governor. Right. So in this chapter, we will study detailedly about all these types of governor. Right. What governor, and then Porter governor, Royal governor, Hartnell governor, Hartung governor, Wilson Hartnell governor, Pickering governor. All these types we will study in this chapter. Right. So this is a simple schematic of a governor. Right. Okay. So there you can see there are few components. Right. So here it is mounted with a bevel gear. Right. So this bevel gear is responsible for the change in the speed. So based on that one, this bevel gear will change the system attached with this one. Based on the rotation of this bevel gear, either it will be going up, move up, or it will move down. Right. So if it move up, these bolts will rotate kind of high speed. Right. So based on that, there would be a setup which would be connected to the fuel supply, which will control it. Right. So I can show you a basic diagram. So here you can see like very simple schematic of a governor, right? Basic governor. This is actually what governor. Okay. So this is how it will the setup would be, right? So there are two balls, right? So this is connected to the shaft. So when this shaft rotates, what will happen? These balls will rotate like this. Okay. So when these balls rotate like this, either this setup will move up if the speed of the ball increases, or if the speed of the ball decreases, this setup will go down. Right? So this one is connected. This link is connected to the valve which controls the fuel supply. Okay, so this valve controls the fuel supply, and this is shaft. Okay, and this shaft is connected with the gear which will be connected to the level here, right? And this would be going to the steam engine, connected to the steam engine. So rest of the part we don't need it. We just need to know, since this shaft rotates, this will rotate, and therefore this bevel gear will rotate. So the shaft which is connected here, which will rotate. Okay, so when this rotates, right, when this shaft rotates, the ball and the arm, these two will also rotate like this. Okay, and therefore this weight will move either up or down. Right? So when this weight move up or down, this link mechanism, which is pivoted here, if it goes up, this will turn the valve either by this way or this way, which will allow the fuel supply or which will block the fuel supply. Right? So this is how the shaft rotates. Right? So when this shaft rotates, you can see here the fuel supply would be going to the necessary position through this valve. Right? When we increase the speed, right? When the speed is increased, so which means this shaft would be rotating kind of high speed, right? So in that case, what will happen? This sleeve will move up, right? So when this one move up, right? Now you see here, when the speed is increasing, this will move up. So which will in turn change the position of this link. Okay, you see here. So this will go up, right? So what will happen? This link would also turn, right? So you see here, this will turn down. So in that case, it will control the fuel supply here, right? By controlling this valve. Okay. So this is just like very basic schematic video I found, but I have some other videos also, the real working, or you can say the animation or working also, right? Both the videos are available. So when I show you, you will understand it much better, right? So this is the basic idea, right? Basic idea of the governor. So this is a what governor, right? This is a what governor, the first type we saw, right? So this is the basic idea of how and why we use the governors, right? Okay, so what we saw now is the what governor, right? What governor. So we'll see what are centrifugal governors. I already told you there are two types of governors, centrifugal governors and inertia control governor. We'll now see what are centrifugal governors, right? The centrifugal governors are based on the balancing of centrifugal force on the rotating balls by an equal and opposite radial force known as the controlling force, right? So in order to explain this thing better, I will show you the working animation of it, right? So now you can see, right? So this is a experimental setup, okay? Experimental setup. So this is the working principle of governor, right? So when we increase the speed, the rotation speed of this shaft increases, and therefore the arms which are connected with that shaft will increase, the speed of that will increase, and therefore the balls will rotate at high speed. When the speed is high, what will happen? The setup will move up. Why is that? Because of the centrifugal force. We know centrifugal force is a force which is acting outwards, right? On the balls, right? So when the force act outwards increase, what will happen? This whole setup will move up. Okay. And when we reduce the speed, you see, when we reduce the speed, what is happening? The total system or this system is coming down, right? So in minimum speed, the balls are almost at the bottom spike, and it will reduce the speed of the rotation of this setup, right? So this is how the working of the centrifugal governor is, right? Centrifugal. That's why the name is centrifugal. Right? Based on the centrifugal force, the principle is made. Right? So when we increase the speed of rotation, the shaft rotation will increase, and therefore the centrifugal force on these two balls will increase, which will make the shaft to move upwards, right? Or sleeve to move upwards. And when we reduce the centrifugal force again, right? And therefore this will come down, right? And that is why the name is called centrifugal governor. So the action is completed by virtue of centrifugal forces, right? And that's why it is called as centrifugal governors. So centrifugal governors are based on the balancing of centrifugal force on the rotating balls by an equivalent or opposite radial force known as controlling force, right? So that controlling force is the equivalent opposite force. The controlling force is provided either by the action of gravity, as in watt governor, or by a spring, as in the case of Hartnell governor. So when we see each governor, we will see what type of controlling force is acting on it, right? It consists of two balls of equal mass, right? As you can see, there are two balls which are attached to the arms as shown in this figure, right? They are attached to the arms as shown in this figure. So these are the arms, and these two balls, they are attached to the arms of these they are attached to the arms, and they are of equal mass, right? These two are of equal mass. These balls are also known as governor balls or fly balls, right? So they can either be called as governor balls or fly balls. The balls revolve with a spindle which is driven by the engine through bevel gears. So as we have now seen in the video, they are connected with the bevel gear, and when the balls revolve with the spindle, that is driven actually by the bevel gears. The upper end of the arms are pivoted to the spindle so that the balls may rise up or fall down as they revolve about the vertical axis, right? So upper end of the arms are pivoted on the spindle, right? So as you can see here, the upper end of the arms are pivoted to the spindle, right? So when the spindle rotates, these arms will also rotate, right? So when they rotate, this may move up or down, the sleeve may move up or down. The arms are connected by the links to a sleeve which is keyed to the spindle. This sleeve revolves with the spindle but can slide up and down, right? So this sleeve, this is a thing, so which may move up or down based on the lift of these links, right? So if the speed is high, this may move that side, this may move this side. So this will move up, right? So this sleeve may move in this range, right? The bolts and the sleeves rises when the spindle speed increases. So as we can now, as we saw in the video, so when the speed increases, the bolts and the sleeve will rise, and falls when the speed decreases. Right? So when the speed decreases, the bolts would fall. In order to limit the travel of the sleeve in upward and downward directions, two stops S are provided on the spindle. Right? So as we can see in this diagram, there are two stops S and S. So which will limit the movement of the sleeve in this range, right? So this is actually the range of the fuel supply for this type of governors, right? So every governor has its own sleeve and also the stop, right? So it depends on which type of governor we are using. The speed variation will also occur, right? The sleeve is connected by a bell crank lever to a throttle valve. Okay. So here you can see the sleeve is connected with the bell crank lever to a throttle valve. Right. So when this throttle valve, when this sleeve move up or down, this bell crank lever would be tilted either this way or this way. Right. Based on that, this will tilt the throttle valve either open position or closed position. Right. The supply of the working fluid decreases when the sleeve rises and increases when it falls. Right? So when the sleeve rises, right? The supply of the working fluid will decrease, right? When the load on the engine increases, right? When the load on the engine increases, we know the speed will decrease. The engine and the governor speed decreases, right? So when the load increases, speed will decrease. This results in the in the decrease of centrifugal force on the bolts, right? So we know if the load increase, the speed will decrease. If the speed decrease, then centrifugal force will also decrease, right? So if the centrifugal force decrease, we have now seen in the video, the bolts will fall, right? Hence, the bolts move inwards and the sleeve moves downwards, right? So if the load increases, if the load decreases, no, if the load increases, the speed will decrease, right? If the speed decreases, then the bolts move inwards, the sleeve would fall downside, right? The downward movement of the sleeve operates a throttle valve at the other end of the bell crank lever to increase the supply of working fluid, and thus the engine speed is increased, right? So when the sleeve move downwards, right? When this sleeve move downwards, what's happening? This results in the decrease of centrifugal force on the bolts. Sleeve operates at the throttle valve, right? When this one falls down, it will operate this throttle valve through this bell crank lever, right? So the movement of this one up or down will move this bell crank lever either by this way or this way, right? So which will control this throttle valve either by tilting it to open the fluid flow or to close the fluid flow, right? In this case, the extra power output is provided to balance the increased load, right? So by increasing the fluid, it will balance the increased load. So when the load increases, since the speed will decrease, so then once it provides the extra fluid, right, then the balance would occur. When the load on the engine decreases, right? So this is the other condition. When the load on the engine decreases, the engine and the governor speed increases, right? So when the load decreases, the engine speed increases, which results in the increase of centrifugal force of the bolts, right? So then it will lead to the increase in the centrifugal force of the bolts. Right? So when the load decrease, engine speed increase, and if the engine speed increase, it will also increase the centrifugal force of the bolts, right? Thus, the bolts move outward, right? So we know if the centrifugal force increases, then the more bolts will move outwards, right? And the sleeve will rises up, right? So if the load decrease, then the speed will increase. If the speed increase, then these bolts will move outwards, right? So if you have seen in the video, these bolts will move outwards. So if these bolts move outwards, the sleeve will move up, right? The sleeve will move up, okay? Thus, the bolts move outwards and the sleeve rises upwards. This upward movement of the sleeve reduces the supply of the working fluid, right? So since already the speed is increased, what now we have to do is to reduce the speed. So what this bolts will do, these bolts control the link mechanism here, right? Bell crank lever mechanism and reduce the fluid supply. This upward movement of the sleeve reduces the supply of the working fluid and hence the speed is decreased. In this case, the power output is reduced. So by reducing the fluid supply, the power output is reduced. So this is how the uh, governor balance the speed, right? So in simple terms, right, so there would be two conditions, right? Either the speed increases or the speed decreases, right? So if we consider the load, right? If load increases, what will happen? The speed of the governor, speed of the engine will decrease. Okay. If the speed of the engine decrease, the centrifugal force on the bolts will also decrease, right? So if the centrifugal force decrease, the bolts will fall down. Therefore, the sleeve will also move down, right? Sleeve will also move down, right? So when this sleeve move down, this bell crank lever would be activated and the fuel supply would be increased, right? So when the fuel supply is increased, now the speed will also again increased, right? So this is the condition if the load is increased. And condition number two, if the load is decreased, right? If the load is decreased, we know if the load on the engine is decreased, then the speed will increase. right? Speed will increase. If the speed increases, the centrifugal force will also increase, right? Centrifugal force will also increase. So if the centrifugal force increases, this ball will move upward, right? The ball will move upward, and therefore the sleeve would be move upwards, right? So the sleeve will move upwards, right? And if the sleeve move upwards, this will activate this bell triangle lever, and what will happen? The fuel supply would be reduced, right? So if the fuel supply is reduced, then the speed will also again reduce, right? So you see here, the speed was increased and it is controlled by reducing the speed. Here the speed was reduced and it was controlled by increasing the speed, right? So this is how the governor functions, right? So this is common for all type of centrifugal governors, but there are minor, like how do I say, changes in the weights or links. So that kind of things are there. That's the difference between each type of governors. But this is a common phenomena or working idea mechanism of a centrifugal governor. Okay. Right. Terms used in governors. Okay. First one, the height of a governor. The height of a governor, it is a vertical distance from the center of the ball to a point where the axis of the arms intersect on the spindle axis. It is usually denoted as H, right? So in the diagram we can see it is the distance between center of the balls to the connection of the arms, right? Intersection of the arms. So this one and this one are two arms. This is the intersection of arms. So this level and the center of the ball, this level. So this distance is what called as the H, which is the height of the governor, right? So that is called as the height of the governor. Second one, equilibrium speed. Equilibrium speed, it is the speed at which the governor balls, arms, etc. are in complete equilibrium, and the sleeve does not tend to move upwards or downwards, right? So this is what called as the equilibrium force. And we know that the term equilibrium means these parts are staying at rest, right? In kind of equilibrium. So they don't tend to move upwards or they don't tend to move downwards, right? So that's what mentioned here. It is the speed at which the governor balls, arms, all are in complete equilibrium. And the sleeve does not tend to move upwards or downwards, right? So in the video, if you have seen, right, so it can be seen like the equilibrium condition can be seen here. So when you see here, right, so now it started to rotate. Now it is increasing, right? Now the speed is increasing, right? Now the speed is increasing, right? Now it is decreasing and increasing, okay? And if you see at a particular stage, right, at a particular stage, we can consider it as equilibrium when the upward and downward movements are not tending to force the sleeve either up or downwards. You see here now, right? Now the sleeve is not tending to go downward, neither going upwards, right? Similar with the case of boards, they are rotating at this particular position, right? So this is what called as the this is called as the equilibrium position, right? This is the equilibrium position, right? So the ball, sleeve, arm, everything in complete equilibrium, which is called as the equilibrium speed, right? And then we have mean equilibrium speed. This is the speed at the mean position of the balls or at the sleeve, right? So mean position, we know the mean position, right? So this is the speed at which the speed is occurring on the mean position of the balls or the sleeve, right? Then the maximum and minimum equilibrium speed. The speeds at the maximum and minimum radius of rotation of the balls without tending to move either way are known as the maximum and minimum equilibrium speeds, right? So the speed at the maximum and minimum radius. So if you take this diagram, right, the radius, right, the radius is the radius between this ball and the shaft, right? So with the increase or decrease in speed, this ball may either move this way or it may move this way, right? So if it moves that way, the radius will increase, right? If it moves this way, the radius will decrease, right? So the minimum radius where the equilibrium can be achieved is the minimum equilibrium, and the maximum radius at which, right? So the maximum radius could be something somewhere here, right? So that maximum radius is the maximum equilibrium, right? So at this maximum and minimum positions, the balls won't tend to move either up or downwards. Okay. Note, there can be many equilibrium speeds between the mean and the maximum and the mean and the minimum equilibrium speeds, right? So the equilibrium speed need not to be only one. There could be many equilibrium speeds, right? For example, if we take this video, right, there you can see that is just an example position where the speed is at equilibrium, right? So this is just a position where the speed is equilibrium. If you reduce this one, it will come somewhere down here and will also be in equilibrium. Now you see here, it is now also in equilibrium. Previously also it was in equilibrium, and here now also it is in equilibrium, right? So there could be many equilibrium speeds. You see here. So after reducing it, this is also equilibrium speed, right? It's rotating at the same level, right? The balls are not tending upwards, tending to move upwards, neither tending to move downwards, right? So this is also equilibrium speed, right? So there can be many equilibrium speeds, right? Either somewhere here or somewhere here, anywhere we can have the equilibrium speed, right? So that's why it's mentioned. It can be many equilibrium speed, need not to be only one. Okay. And then we have some term sleeve lift. It is the vertical distance which the sleeve travels due to the change in the equilibrium speed, right? So vertical distance a sleeve travels. So here is the sleeve, right? So this may travel upwards if the speed increases. This may travel downward if the speed decreases. So this movement, right? This length is the sleeve lift. It is the vertical distance which the sleeve travels due to the change in the equilibrium speed, right? So these are certain terms we use in the governors, right? Okay. So these are few terms, and these are few. Uh, you can say the nomenclature, or you can say the markings. Usually standard markings, right? So the height we usually go for h, right? And the radius, that is r. Okay. Between the ball and the shaft, it is r. And the weight, right? Weight of the ball, we make it as W or mg. Then Fc, this is centrifugal force, right? Centrifugal force which tend to act outwards. That's why it's marked this way, Fc, centrifugal force. And here is the tension, right? So since there's an arm and there's a ball, there should be some kind of tension, right? So these are few terms we usually use in governors. And there's an omega, right? Omega is the angular velocity, you know, right?